As I said, I am speaking about a particular unsupervised task, which is the generative one. So we want to feed a machine with data that here it will be digits. We want it to learn and to generate new data that is as close as possible at the one that initially digested. Okay, this can be done with many different methods in the literature. My talk will be mostly concerned the energy-based models, but there are also the GAN, the variational coders that are a lot more fashionable these days. But okay, so we will center on the energy-based models. As I said, we want to feed the machine with data, and in this talk we consider different kinds of data. It can be images, it can be genome, it can be proteins, the sequences of protein families. It can be just data points forming clusters, or it could be even Ising configurations. Okay, so in the energy-based models are quite familiar to us physicists, and the idea is that we want to assign an energy function to the data so that we can feed the parameters of this energy function, so that the typical configuration in terms of the Boltzmann probability, the equilibrium ones, look as much as similar, as close as possible to the original data set. Okay, this is normally done through maximum, through maximization of the log likelihood. That the idea is just this: we want that the probability of finding, I mean, in the marginal probability of observing certain data, it's maximal. Okay, this function, we cannot compute it analytically because it's untractable, especially because we don't know the partition function, obviously, the same problem that we have in physics. So normally the problem of this method is that in order to train it, we need to sample. And this we do it with Monte Carlo, and this is quite slow. Okay, the energy function of these models can be essentially whatever. We can have a bipartite network that is the restricted Boltzmann machine, but we could have something deeper, or even something very complex with convolutional layers and very, very deep. Okay, why do I want to focus on restricted Boltzmann machines? Especially because they are essentially a disordered Ising model, and I'm a statistical physics and we like the Ising model. And because we can obtain, once we train, we have the empirical distribution of the data. And since we had a very shallow network, we are going to be able to try to analyze what the machine learned. Okay, and also they have a nice property that is being used recently quite a lot, as this, and it's that it can be trained with few data, which is useful, especially when you have, for instance, experimental data, or for instance, in the sequencing context, because now we have very large databases of, for instance, in proteins here, of protein sequences that we don't know the functions, we don't know the structures, so we can try to learn from this. And maybe these databases are not that large. So restricted Boltzmann machines are being appeared as a very nice object to extract biological information from them. Okay, this is the good part of the restricted Boltzmann machine, but there are other things that are not that nice, and especially because training RBMs is quite hard. I mean, anyone that has tried to do it, for instance, if you try to learn digits, would you often end up generating just ones or just six, or very capricious things that you don't understand. It can be that you train well a machine, but later when you want to generate new data, it takes you forever, so it's not very practical. And one of the main problems is that there are no implementations for convolutional layers in RBM. But in any case, just a bit of history, the RBMs have been around for quite a lot of time. They were proposed by Smolensky and later were popularized by Hinton. They had the goal era in the 90s when they were used as pretend units for more deep more or less 15 years ago, they are getting into disuse because there are other models, generative models that perform better. In parallel, from the statistical point of view, it's the moment in which we start to have quite a lot of understanding of these models. Now we have phase diagrams for RBMs. We understand quite a lot on the learning dynamics, how the patterns are encoded in the machine. So if we want to propose methods to extract information, these are very suitable. And we have, for instance, message passing algorithms. Okay, the restricted Boltzmann machine, as I said, is essentially an spin. Okay, we here have just binary variables, and it's in model in which we have two bipartite layers. We have the visible ones that are going to correspond to our data, for instance, the pixels of the digits, and we're going to have a hidden layer that is trying to catch the correlation present in the data. Okay, now if we want to maximize, as I said, we are going to have a data set that it could be, for instance, digit, and we want to find the parameters, the W, eta, and zeta, that maximize the probability, the marginal probability of observing precisely the data set. In the RBM, the gradient of the log likelihood is quite easy to write. We have the positive part, and we have where we have the average of certain observables over the data set. This is easy to compute. And we have the second part, the negative one, in which we have to compute the same observable, but average on the Boltzmann measure of this model that is going to change in time. So this is costly, and I will come later. Just to make a summary, we have two different states. We are going to have a training stage in which we feed the machine with data and we feed the parameters. And once we have the parameters, we sample the equilibrium distribution of this model and create new data. In both stages, we are going to need to do sampling because in order to feed the parameters, we need to do sampling to compute the gradients. So we have samplings in the training and in the generating part. Okay, so as I said, I'm going to talk a little bit, but just briefly on the possibilities for interpretability of the RBMs. I don't have a lot of time to talk more, but the idea is that, okay, for instance, in the model I was presenting before, if we now integrate the latent variables, the hidden variables, we can get an energy function for our data. And if we expand this, we can see that we have an energy function that is going to have interactions to all the bodies that we want. So it's in principle a model that can catch all the interactions up to any level, which is quite strong. One of the nice things that we have been working is that it's actually possible to find a expression for each of these tensors or matrices or even the fields to extract it from the parameters of the network that we have already learned. And in fact, we can do quite nice inference of it. For instance, we can train it with Ising-like models with interactions, two-part interactions, three-part interactions, or even field, and we can reconstruct quite well the coupling. This is a work that will be coming soon, I hope. Okay, once we have the energy function, of course, you can try to study dynamics, you can try to study many other things. Okay, so now I come to the problem of training RBMs that I was saying before that is fastidious. I mean, controlling the training, it's hard. And the reason it comes precisely from this negative part of the gradient that I was presenting before. Okay, so to compute this part, since we have a model that is changing through the training, we need to compute it every time, and we do it with Markov chain Monte Carlo that we know that you can always create samples according to a given distribution as long as you do quite enough steps. So how long it took? Okay, there is an error here. This should be higher than thermalization time. So we know that this Markov chain process is going to work if we do enough steps. If we don't do it, we will be generating samples with another probability. One of the problems is that in general, we have to repeat this process many times during the learning, because each time that you update the parameters, you have to compute the average of the model, and you want to update the parameters many times. So this is very costly. Okay, we just do some few steps and let's hope it works. And we can try to improve the thermalization by finding good initial configuration. So if I start nearby the equilibrium, okay, with some few steps, it should be okay. So there was the contrastive divergence proposed by Hilton that actually popularized the use of restricted Boltzmann machines, in which the idea is, okay, we don't know which are the equilibrium configurations of the model, but if we do it well, it should be more or less like the data set. So let's initialize its chain at the data set and just do some few steps. He was proposing one, but okay, let's say 10 steps and compute the gradient. You can do something better, that is the persistent contrastive divergence, that is saying, okay, since we are changing the parameters very slowly, we can just take the configuration as the previous last configurations that we had from the previous update. So this should be more or less better, like some kind of simulated annealing. And there have been other proposals, for instance, to try to use belief propagation to infer the minima. Or one could go deep in other algorithms, like doing parallel tempering that has been done, or simulated annealing to compute it. What we found quite extensively in a lot of data sets, in this word here, is that actually the number of steps that you do here has a very strong impact in the models you get. If you use a number of steps that is not enough to equilibrate, you end up with models that they have memory. Actually, what they learn is to reproduce exactly the same dynamics that you use to train it. While if you do in equilibrium, okay, this model behaves as you were expecting to do. I mean, so you get a model whose equilibrium configurations are similar to those of the data set. Okay, let me explain you a bit what we mean with learn the dynamics. And the idea is, okay, so we have our RBM that is going to be trained for many steps. This means changing the parameters. And for each step, we need to do a Monte Carlo simulation to obtain the gradient. Okay, so the idea is, okay, after a moment of the training, we can take the machine and do a sampling to get the equilibrium configuration. What we see is that if you train the machine with certain dynamics here for certain number of steps, you're getting good configurations when you repeat the sampling exactly following the same procedure. Same initialization, same rule for steps, and same number of steps. For instance, here I show you some figure that we did with different data sets. Here we have the sampling times in which they are even spaced in logarithm scale. So these are much more steps than previously. And what we see is that, okay, we initialize the chains at random. Okay, we get models that get configuration that get better and better and better. And the point is that in particular, they get better until they get the number of times that we're used to train. This is a model where we are doing the training, and this was the training. So the model remembers how many steps you did. And the thing is that we get configurations that are better also because they have a lot more variability. If we continue later, we get like a thick version of the same extents, and also a frozen version. Once we get in configuration, you stay there more or less forever and get a very thick or biased version of the figure that we had before. This has a lot of consequences. If we are learning the dynamics, it means that if we train the machine with one dynamics and we later sampling with a different dynamics, this is not going to work. For instance, if we train a machine using the contrastive divergence regime, for instance, we start with digits, we do some steps, and we train the machine like this. If later we do a sampling with this machine, started from a random configuration, and we start to do sampling, we basically find nothing. We don't get any number or whatsoever. We can say, okay, I was saying before that you have to repeat the dynamics. Since we change the initial configuration, we can also try. If we do this, okay, we start from numbers. Now we do sampling. Okay, at a certain moment, we have numbers and they disappear. So at least from this talk, it's quite important to remember that especially if you don't thermalize, doing contrastive divergence is very dangerous because you get models that do not match the data set at all. I mean, this was actually pointed out in several works in machine learning years ago, but in physics, you find still nowadays a lot of people using contrastive divergence, and it's dangerous unless you do equilibrium. Okay, we can also not only changing the initial configurations, we can actually change the rules we do for the sampling. For instance, if we train the machine using mean field updates, if now we take this machine and we sample using standard Glauber heat bath updates, we see that again, we don't get numbers. But if you repeat exactly the same update rule, you now sample using mean field, you do find numbers. But again, you find numbers that stay there forever, and probably we did take something much longer. At the end, it will be just ones because there is quite a tendency to end up with ones. Okay, this was done just with figures, but we can quantify this quite well. We can obtain different observables to measure how good the samples are. And what we see, okay, here we were comparing the covariance matrix or the Fourier coefficients of the generated samples, and this is the error. So the lower it is, the better it is the samples generated. And if we use a machine that it was trained starting from random, doing 10 steps and so on, we see that the best configurations are found exactly when you do 10 steps. And when you go further that way, you start to get configurations that are much worse. This explains why when you do training a restricted machine, you can find things that you don't understand, very weird results, because either you match the same sampling procedure or you get basically whatever. Okay, this was done with a machine training with 10 steps, but if you do it with 100 steps, you get the best quality at 100. If you do it with 1,000, you get it at 1,000 and so on. So the machine remembers how it was trained. The machine has memory, it's clearly out of equilibrium, and it's also a very slow machine because we get things that are still evolving in time for a very long time. Just to compare what it will happen if we had trained the machine in equilibrium, it's more what you would expect. You get a machine, you start to do sampling to find equilibrium. Okay, the different colors have different number of updates of the machine, but at least for the speeds, it was not very important. But what you get is, okay, you get something that evolves in time and at a certain moment converts to equilibrium and continue. If we plot the samples, this is not longer in log scale, this is linear scale. Okay, it takes you some time to generate digits, but from the time you generate digits, if you continue, you generate new digits, not the same digits frozen there, okay? So they behave a lot more as you would expect. So the problems with restricted Boltzmann machine in general come because you are training them in out of equilibrium. Yet, okay, I didn't show data for this, but in out of equilibrium, I showed you figures before, you can actually generate quite well. I mean, if your goal was to generate samples, it's probably the most efficient way of doing it because we can even compare the quality and you generate better samples if you exploit the memory effects than if you do equilibrium thing and explore the equilibrium state. So the out of equilibrium, it's faster to train and it's optimal to generate new samples. And it was actually already realized in generative ComNets some few years ago that it was the most efficient way of generating samples. They were even claiming that they could compete with GANs following this procedure. And it has been also checked recently in Boltzmann machines, and they also generate better. So it seems to be a property of energy-based models in general, not just the restricted Boltzmann machine. But as I said, you get models that are clearly not good models for the data because the equilibrium has nothing to do with the data. So one can wonder how to do the equilibrium that in principle should be lead us to what we wanted to go, to get a model for the data. The problem is that, okay, we want to do brute force. This means that we have to do very long samplings. So let me move to how we train in equilibrium. And the question is, okay, we want to do equilibrium, how long it would take us to do it? Okay, we can try to estimate the relaxation times of these systems as function of the number of parameters updates that we get in the machine. Here we have the time correlation function obtained with MNIST, and this is the easy kind of data set. But what we see is that the more you train the machine, the longer it takes to relax. We can compute them. Well, this would be the relaxation time, the mixing time. We can also try to check when do you equilibrate, which should be some few times this time, just checking when it forgets the initial configuration. But the point that we see is something like, okay, at the beginning of the learning, you thermalize very easily. At a certain moment, you get a jump. And later on, you get something that grows as you train more and more the machine. But at least this is feasible. This is long, but it's not too much. Okay, this was MNIST. Okay, this was training with MNIST, with the digits. But now let's see that what it happens when I try to train it with genome database, in particular with the 100 genome human genome database. What we see is that when we try to compute the times, the relaxation times, we pass from just having essentially one step and you decorrelate, and to go something that we don't know what it is, but it's beyond 10 up to the 5 Monte Carlo steps. So we cannot even measure the realization time. So clearly, by brute force, we cannot thermalize here. And you may wonder what it is related. It actually, I mean, it looks like a phase transition, and it is a phase transition. It will be discussed quite a lot more in detail by Aurelian later. And the idea is that, okay, it can be solved in mean field, that the training is triggered by the moment in which we pass from being in a paramagnetic phase to a ferromagnetic-like phase, in which the principal components of your data sets start to get included in the matrix, in the coupling matrix of the RBM. And in fact, it can be tracked by looking at the eigenvalues of the weight matrix. And from the moment it grows, we are going to have the first drop. And in fact, what you see in practice is that your data set is gonna align towards this direction. So we start to find spontaneous magnetization in certain random directions given by the data set. And okay, we can actually see that the times start every time that we have a new eigenvector that grows up, new times in the relaxation times that grow. But Aurelian will talk a lot more on this. So I come back to the problem I was saying before with the genome data set, and we can see what is happening here. So we can project our data through the directions, the eigenvectors of our model. And what you see is that, okay, here it will be the first direction and the second direction we projected. And okay, below the jump, we just have one single cluster. And once it jumps, what we see is the development of two clear clusters. And if we go on, you can eventually get a lot of clusters. So it's clear what is happening here. I mean, it's exactly the same problem that we have with the easy model if you lower down the temperature. When you approach the critical temperature, times are going to diverge with the critical slowing down. But when you go below it, this is even worse because your simulations are getting stuck in one of the minima, in one of the maxima of the probability. And the cost of moving to the other one is building interfaces, and this is rare. So you're gonna get simulations that are getting really, really slow. Okay, so I said before that this happens with the genome, but it was not that strong with MNIST. And one can see why quite easily if you do the principal component analysis of MNIST, for instance, we get data that it's quite I mean, you can pass from one to the other one. While if we do it with gene or we do it with proteins, typically what we get is isolated clusters that are really separated. It's clearly that if we train well a machine, we are getting a model that it's going to have several maxima. We're going to have coexistence states, and we know that sampling with Monte Carlo, a multimodal distribution, is very hard. But we also know more or less in physics how we should do it, at least in nearby first order transition. And the idea is here. So we go back and we started to say, okay, let's try to train an RBM with clusters, point clusters, because it should be the same problem. So we took, okay, this problem in clusters, high dimensional clusters, in which you just have clusters split up in one direction. It was pointed out in a paper recently that this is impossible to learn with a normal procedure of an RBM. And in particular, they had an analytical way of training the machine. So we have an exact machine. We know that it's the good machine for this, or at least a good machine for this data. Okay, here I saw the clusters. We have the histograms when projected to the first component of this data. Okay, what happens if now we take this machine, which is perfectly trained, and we sample it, starting from random. Okay, typically we just get all the points created here. If we wait a lot, we start to find points created here, but we never ever find these other classes unless we start there. If we start there, we stay there, but we get stuck there. Okay, we have proposed another way of doing it with a biased Monte Carlo, in which we can create samples quite, I mean, here we have 10 up to the 5 sweeps in the standard Monte Carlo. We can do it quite fast. Okay, and the idea is precisely, we have a problem of thermalization because we have a problem of coexistence between phases. So if we introduce more constraints in which we only allow to have one of these states, this problem is solved and we can thermalize quite easily. So let's divide our possible magnetizations. We just discretize it at different values. We are going to perform simulations at a fixed value of the magnetization so we can break the coexistence. Okay, this can be done quite easily by introducing these soft constraints, introducing a Gaussian picket around the value that you want, that it should be like the umbrella sampling method, and later you can compute averages in this ensemble, just as usually. So now we have a lot of simulations at different values of the magnetization. We don't have thermalization problems, but the point is how we do reconstruct the original one, because it's the one that we're interested. At this point, what we used was the Tethered Monte Carlo algorithm that it's quite simply to understand. And it's the idea that, okay, we can actually write the partition function as an integral over the constraints of a given magnitude. Well, this would be an alpha that is just given by this term, just because we can always integrate a Gaussian, and that's all. In the same way, if we have the observables in the M-fixed ensemble, we can reconstruct the original ones just by integrating numerically this effective potential. The nice thing of the tethered method is realizing that this effective potential actually can be computed in the simulation by computing its derivative with respect to M. Because if you just compute it, it is going to be the difference between the constraint at the actual value. So if we have the derivative, you can integrate it and obtain the potential and recover everything up to the precision you want, depending on how long you did the simulation. So the idea is this: we compute the gradient, we integrate it, and obtain the well, this will be minus the potential, and you can recover the probability function. And we can see here, I saw the probability we recover. These were the original data, and we see that it fit very well with the original data. Of course, if you have the distribution of PM, you can sample. You can just create new samples just with some few steps. Okay, so now the idea is if we know how to sample properly, we can introduce this in the learning as well. That will mean that we want to compute this using the tethered method. Okay, this we can do it exactly as I was saying. This was for a generic observable. And we can also generalize it to more constraints if we want, because this is automatic. You just get more Gaussians, more discretization points. And instead of computing the derivative, you compute the gradient, but we can reconstruct it as well. So let me just show some few examples. We can start with synthetic. Now we have 2 clusters, and we can train it either with standard Monte Carlo, with the Tethered Monte Carlo. I can tell you directly that with the standard Monte Carlo, you get machines that have 2 clusters, but they are not in the right place. You cannot train it at all. With the tethered, you can. But anyway, if you try to sample using a standard method, this machine, you just get something that gets stuck. I mean, the godicity is broken from the first moment and never jumps. So you cannot measure weight the different probabilities. Okay, here I show you, for instance, okay, this was the data in black. In red, we have the data obtained, the probability obtained with the tethered, and we can see that the one from the standard approach, it doesn't have two peaks. It actually just have 1 peak, but it has two minima. So the simulation was getting stuck there. Okay, we can do it with 3 clusters in 2 dimensions. We get it well as well, the training networks. And the question now is what happens when you go to real data. We can check, for instance, with MNIS, but instead of considering all SNIS, we just consider the 0 and 1s. This you can see with the PCA that it has, again, 2 maxima, and you have all the sample problems that you would have. We can do it with the human genome, and it works well. But what is different with the real data, in contrast with this artificial synthetic data that we were using, is that now you actually can do it also with PCD. It works. It's not, as I was saying before, you can train a machine. Only you get machines that they have extremely slow dynamics. So if you want to test it, you need the tethered to see if the machine is good or not, because you cannot test it in any way. And still, we don't understand really why, but if you train the machine with the tethered, you always get machines that have faster dynamics, relaxational dynamics, than if you do it with the standard procedures. And with this, I finish, I'm sorry. And okay, as I said, the RBMs brings a possibility for pattern extraction, which is quite treatable. The problem is that they are hard to train. We now think that we know how to train them well. If you want to generate samples, you have to exploit the memory effects. If your task is generating, if your task was to obtaining good models, you have to do equilibrium, and we propose a way to do it. Sadly, it has several problems because it breaks the parallelization of the update, so it gets slower, not for the Monte Carlo, but for the practical application of it. And okay, we have 2 words relating to this. This is for the out of equilibrium, and now we have for the equilibrium. And thank you very much.
Thank you very much for the talk. Are there any questions from the audience or online?
Thank you for interesting talk. And one thing that I missed at the end in this whole idea, introducing constraints during the learning phase, is how do you choose the constraints? So is it something that you just decide after looking at the data set? Is there a way to do it automatically?
We were
And-
doing it automatic. In particular, all the data I saw, it was the constraints were just the principal directions of the data set. We just do the PCA and we get the first two that splits the data set. In principle, you could do it also with the principal directions of the weight matrix of the RBM. We know at least this choice, it has to work for the first part of the learning. At a certain moment, it stops to work because you have a lot more important directions to explore. So we will need to fix more constraints, and we cannot do it because it gets too slow. But you could do it in principle, unless someone finds a better order parameter that doesn't have this problem.
Thank you.
Any other question? If not, okay, let's move to the other speaker.